Hi all. Today's class is about Hall effect. So in this class we can see what is Hall effect and what is the expression is used to find the Hall voltage. So first we can define the Hall effect. The Hall effect is defined that when a current carrying conductor is placed in a magnetic field, it will produce a voltage difference, and that production of this voltage difference due to this current carrying conductor in a magnetic field was called as the Hall effect. And this current carrying conductor, current as well as the magnetic field, all are perpendicular to each other. So the Hall effect is defined that when a current carrying conductor is placed in a magnetic field, that will produce an electric field. That effect is called as Hall effect. So the electric field production basically due to the potential difference, and the voltage uh, produced due to this Hall effect is called as Hall voltage. So the Hall effect is the production of a voltage difference, that is the Hall voltage across a current carrying conductor in presence of magnetic field, and they are perpendicular to both this voltage difference. The generator voltage is perpendicular to both current and magnetic field. So we can see what is Hall effect in detail. So when a piece of conductor, it may be metal or semiconductor, carrying a current is placed in a transverse magnetic field, an electric field is produced inside the conductor in a direction normal to both the current and the magnetic field. So it says that when a current carrying conductor is placed in a magnetic field, it will produce an electric field. So if the current carrying conductor is placed along x direction, then the magnetic field is along y direction, then this generated electric field should be in the z direction. That means these three parameters all are perpendicular to each other, and this phenomenon is known as the Hall effect, and the generated voltage is called the Hall voltage. So we can see in figure there is a current that is flowing along OX direction, and the magnetic field is placed along OY direction, so the generated EMF or the electric field should be in OZ direction. So next we can see what is the Hall effect or Hall voltage for a p-type material or an n-type material. So first we are taking our material is n-type semiconductor or metal. So if the strip is made up of metal or n-type semiconductor, the charge carriers in the strip will be electrons. So we know that for an n-type material the majority carriers are electrons. So in this we are taking the current flow in this OH direction, so we know that the electrons will flow in the opposite direction, that means XO direction. That means electron flow and the current direction are opposed to each other. So the conventional current flows along OH, the electron must be flowing along XO. If the velocity of the electron is v and the charge of the electron is minus q, the force on the electron due to the magnetic field can be represented as F is equal to minus b q v, and this force will act along all z directions. So when a current carrying conductor is placed in a magnetic field, and if the material is n-type, the electrons get some force due to the magnetic field, and that force is minus b qv, and that force will act along z direction. So this, due to this force, the electron will be deflected and the electrons will accumulate at the side of AB, the face of ABEF. So we can see that the face ABEF, due to this electron accumulation, become negative, and at the face OCDG becomes opposite. That means it will induce a positive charge on the other side of this OCDG. So we can see that ABEF now negative charge and this OCDG is positive charge. So we can say that one side is negative and another side is positive. So a potential difference is established across the phases ABEF and OCDG, causing a field EH. So we can here minus charges on the ABEF side and a plus charge on the OCDG side, that will contribute a potential difference, and due to this potential difference an electric field EH generated. So this electric field is called the Hall electric field EH. And this field, due to this electric field, there should be another force, that is minus QEH on the electrons in the opposite direction, that is in the y direction. So now this due to the current carrying conductor placed in a magnetic field that will produce an electric field EH, and due to this electric field the electrons may undergo another force that is minus QEH, and the direction of that force is y direction. So at equilibrium condition, these two forces, that means force due to electric field and force due to magnetic field, balanced each other. So we can say that QEH minus QEH is equal to minus BQV, or from this we can write EH is equal to BV. So that's the first equation, that is the generated electric field due to this Hall effect is equal to B into V. B is the magnetic flux density and V is the drift velocity, or the velocity of this electrons. And if J is the current density, then we can write J is equal to, we already studied that the expression for J is minus NQV, where N is the concentration of current carriers. So we can write V is equal to J by minus NQ. Then we are replacing the value in equation EH is equal to BV. This V equation we are replacing in the in EH is equal to BV. So you will get EH is equal to B into V. V now J by N minus NQ. So our electric field equation is BJ by minus NQ. The Hall effect is described by means of the Hall coefficient RH in terms of current density J by the relation EH is equal to RH BJ. So the density and this electric field is related like us. This EH is proportional to B into J, and that proportionality constant is RH, and this is called Hall coefficient, or we can say that RH is equal to EH by B. J. We can replace the EH expression as we obtained earlier. So that is BJ by minus NQ. So you will get RH as BJ by minus NQ into BJ. So BJ cancels. So remaining is minus 1 by NQ. And Hall field is proportional to current density and magnetic field. The proportionality constant RH is called Hall coefficient. So already we said that the field generated due to this Hall effect is always proportional to the strength of magnetic flux density and this current density. The magnetic field as well as this current is depend on this. The electric field is depend on this magnetic field as well as the current. They are directly proportional to the magnetic flux density B and the current density J. So we can write the proportionality constant as RH, and it is called Hall coefficient. And all the three quantities EH, J and B are measurable, then the Hall coefficient RH and hence the carrier density N can be found out. So this EH we can measure, B we can measure, and J we can measure. So from this we can measure RH. If we are getting this RH, we know what is the value of Q, then we can easily find the carrier concentration N using the equation N is equal to minus 1 by RHQ. This negative sign indicate that our material is N-type material. Next we can take our material as a P-type semiconductor. So if the strip is a P-type semiconductor, the charge carriers in the strip will be holes. So we know that for a P-type semiconductor, the majority charge carriers are holes. So we can see that if the direction, conventional current flow direction we took as OH, so the hole also will move in the same direction as that of conventional current. That means holes will move in the same direction, OH direction. So we can see that if the charge of the hole is Q, then the force experienced by the hole due to the magnetic field we can represent as F is equal to BQV, and which act along offset. So due to this force, the holes will accumulate on the face A, B, E, F and create a positive charge. So the holes will left from this OCDG phase, so there should be a negative charge. So one side is positive and another side is negative, so that contribute a potential difference, and due to this potential difference electric field created. So for a p-type semiconductor we can represent this Hall coefficient RH is equal to 1 by PQ, where P is the Hall carrier density. Next we can find the Hall coefficient in another way. So the Hall coefficient is determined by measuring the Hall voltage that generate the Hall field. So how we can measure the Hall coefficient from the Hall voltage. So we already said that when a current carrying conductor is placed in a magnetic field, it will produce a potential difference, and that potential difference is called as Hall voltage. And if W is the width of the sample across which the Hall voltage is measured, then we can say that the electric field is equal to Hall voltage divided by W. And RH, we already said that it is EH by BJ. So we can replace EH as VH by W. So we will get RH as VH by W BJ. From this we will get the Hall voltage as RH W BJ. Next we can take the thickness of the sample as T, the cross-sectional area A. Then A is equal to width into thickness, that is WT. Then we can write the current density as current per area, or I by WT. Then we can replace J here as VH is equal to RHWBJ. In that J we are replacing as I by WT. So you will get VH is equal to RHWB I by WT. So you will get it as RHIB by T, where T is the thickness, or from this we can find RH is equal to VHT by I into P. So we know what is I, that is we are giving the current and we are selecting the magnetic field strength. Then T is the thickness of that sample. So after this there should be a potential difference generated, that is called VH, and we can easily measure VH. Then from this fact VHT by IB, we can find the RH Hall coefficient easily. Then VH will be opposite in sign for P and N type semiconductor. So we can write the expression for Hall coefficient as VHT by IB meter cube per coulomb, and this VH is the Hall voltage, T is the thickness of sample, I is the current, and B is the magnetic flux density. Similarly, we can also find the conductivity or mobility for the N-type material as well as P-type material if we know the Hall coefficient. So we can say that the conductivity sigma N equal to NQ mu N for an N-type material. From this mu N we can write as mu N is equal to sigma N by NQ, where minus 1 by NQ is the Hall coefficient for an N-type material. So we can write mu N as sigma N by NQ, which is equal to minus sigma N into RH. That means mobility mu N is equal to minus sigma N into RH. Similarly, for P-type materials, this sigma P is PQ mu P, or we can write mu P as sigma P by PQ, where 1 by PQ is RH. So we can say that mu P related as Hall coefficient in such a way that mu P equal to sigma P RH. And next we can see what are the applications of this Hall effect. So after finding this Hall coefficient, we can check whether it is a P-type material or an N-type material. For an N-type material, the Hall coefficient is negative, whereas the P-type material, the Hall coefficient is positive. So this, from the direction of the Hall voltage developed, one can find out the type of semiconductor. So if we know what is the value of Hall coefficient, we can easily find whether it is a P-type or N-type material. For an N-type material, the Hall coefficient is negative, and for a P-type material, the Hall coefficient is positive. And the next application, we can calculate the carrier concentration. That means we can find the carrier concentration of electrons and similarly holes, because N equal to 1 by QRH for N-type material, and P is equal to 1 by QRH for P-type material. So we can easily find what is N and what is P. So next, if we know the Hall coefficient, we can easily find the mobility of the material. That is the mobility mu N is equal to minus sigma N RH for N-type material, and mu P is equal to sigma P RH for P-type material. And next application is we can easily measure the magnetic flux density. So if we know the RH value, that means the Hall coefficient value, then we can easily find the magnetic flux density. B is equal to VHT by RHI. VHT by RHI, where VH is the Hall voltage and I is the current, T is the thickness, and RH is the Hall coefficient. So these are the different application for Hall effect. So in next class we can see one example related to this Hall effect.